Bueno, vamos a dar inicio a nuestro seminario Sandoval Vallarta de esta semana. Es un placer tener aquí a Isabel Cordero Carrión, de la Universidad de Valencia, España. Isabel es licenciada en Matemáticas y doctora en Astrofísica por la Universidad de Valencia. Ha sido investigadora postdoctoral en el Instituto Max Planck de Astrofísica en 𝗥𝗲𝗀𝗂𝗵𝗵, en Múnich, con una beca de la Fundación Humboldt, y en el Observatorio París-Meudon, en Francia, con un contrato propio del observatorio. Ha también sido investigadora visitante en las universidades de Lieja y Namur en Bélgica. Actualmente es profesora en la Facultad de Matemáticas de la Universidad de Valencia en el área de matemáticas aplicadas. Además de su labor docente, obviamente que lo combina con una actividad de investigadora en matemáticas aplicadas y en astrofísica, que es justo de lo que nos va a hablar, con especial interés en relatividad numérica y ondas gravitatorias. Es miembro de la colaboración internacional Virgo en Valencia y actual coordinadora de divulgación de toda la colaboración. Ha sido miembro de la Junta Directiva de la Sociedad Española de Relatividad y Gravitación, gestora de comunicación científica de la Acción Europea 𝗥𝗲𝗀𝗄𝗏 sobre ondas gravitacionales, geofísica y machine learning. En 2019 recibió la beca Simons Emmy Noether del Perimeter Institute, felicidades, para una estancia de investigación que realizó en 2022 por la pandemia.
Exacto.
Y además dedica su tiempo y esfuerzo a luchar por la igualdad y la diversidad en el mundo académico, así como para la divulgación y comunicación científica. Y ahora nos va a hablar precisamente de su área de 𝗣cia, que son aplicaciones recientes lo voy a decir en inglés, Minimally Implicit Runge-Kutta methods in astrophysics, con énfasis en the RRMHD equations and M1 neutrino transport equations. Adelante.
Muchísimas gracias. Thank you very much. I will switch to English since there are some international guests in the room. It's a pleasure. It's really a pleasure to be here. Thank you, Miriam. Thank you, Eduardo. Thank you, everyone who made possible to give this seminar here in person. Let me just mention, I am part from the University of Valencia. If you have visited Valencia sometimes, you may recognize this symbol here. When I go out of Valencia, people say, why you are putting this Batman here? It's nothing about Batman, it's nothing about Hollywood, but the bat is the symbol of the city of Valencia. So if you are supporters from Valencia, Villarreal, Levante, or other soccer teams, you may find this bat everywhere. So why not in research? And since we do gravitational waves, so the bat is generating gravitational waves, of course. There is more story about this logo, but I also have this artistic part in research. And we are the group in Valencia, member of the Virgo collaboration about gravitational waves. And as Miriam also mentioned, I am pushing a lot of effort in trying to have a more diverse and fair environment in academia. So it's really nice to see a lot of women here, really. That's not the case always. And I am pretty sure that we need a more diverse and global point of view, also in research, and also because of mental health. So this is the Asociación de Mujeres Investigadoras and Tecnólogas in Spain. There are several nodes. And for example, we fight in order to take into account things, normal things maybe, but since just the last call of the Sexenio de Investigación in Spain, just the last call took into account that maybe you have been father or mother in your life, so this should be included in the productivity, let's say, of your academic life. Maybe this is so obvious for you, but not for all the governments, in particular not in Spain. And yes, I do a lot of these things too. Actually, this is a very boring slide, so I'm going to put the cool one because you did a so cool poster. And you may notice that I have included something in the poster. And well, if you go to a restaurant, you have this Estrella Michelin. So 3 Michelin stars is like the super red. So I was able to participate in this seminar twice before today, but only in online mode. So these are my 3 𝗙𝗲𝗰𝗵 stars, so I think I now deserve to have some international recognition. So my proposal here is that you should point this participation in seminaries 𝗙𝗲𝗰𝗵 as a merit in your CV, like Michelin stars in the merits of the restaurant. So this is really to try to show you how thankful I am to be here. It's really a pleasure. I also want to mention one thing before I start, let's say the academic and the project I want to show you. It's not always the case that when you go to a seminar of a particle physics or physics group, they are open to something different from their area. And I think that's very important. I don't pretend you to be expert in applied mathematics. I would like just to share with you some ideas. Maybe someday, I don't know, you are doing something. I may need something from people doing applied mathematics. So there is people in applied mathematics willing to collaborate with other people in other areas. Just try it. We are a few, not everyone, but we are a few people open to collaborate. And I also think we should collaborate more between different areas. It's not that I want or I can become an expert in particle physics, but maybe some of my expertise can help you, and also some of your problems can motivate people in my area. So let's say fraternity message. Let me now start with the talk, with the seminar. So this is basically the outline I want to do. The goal of this talk is to show you how this idea, this minimally implicit Runge-Kutta method, this scheme, can be applied in order to numerically solve hyperbolic system of partial differential equations with a stiff source. And this is something that in particular is very relevant for some astrophysical scenarios. I am part of the math faculty, but my research group is in astrophysics. So let's say I am the mathematician of the group trying to help with this development of numerical methods. I will not follow the traditional mathematical way of defining the method and then showing the applications, but I will start showing you two applications, and then I hopefully will be able to give you the general idea of the method and the potential additional applications that you can think about. And the first example is the so-called relativistic, resistive, magnetohydrodynamic equations. So there are a lot of things coupled there. This is all the results I'm going to show are part of a publication, recent publication of this year, with the collaboration of now recently doctor since 2 weeks under my supervision. Is the first doctor under my supervision, Samuel Santos from the University of Valencia. And Clara was a student in the faculty, and she started this project in her final degree project, and I promised her she will be included in the publication, even if the publication arrives 2 years later. But I want to credit all the people that collaborated in this project. So she's nothing to do now with research. I think she's teaching in high school, but she has a scientific publication because she deserves. Then the second example is the so-called M1 neutrino transport equations. I will give more details about what this M1 means. Basically, this is important in supernova applications. Part of the contents I'm going to show can be found in this archive reference. I want to say these things because it's not only about science, but how science works. This article was submitted to a journal and immediately rejected. And I was like, okay, this happens, don't take it too seriously. Let's put this in archive, so if someone is interested, they can check it. In the meantime, Samuel, again, the doctor under my supervision, and Martin Obel-Gaulinger is another postdoc collaborator in Valencia, in the Department of Astronomy and Astrophysics. And it was rejected, but we uploaded it in archive. And in less than 1 week, people from Italy, Germany, and USA were interested. So I say, you are not the referent, but no problem. this support encourages us to include additional material, and we are trying to submit it again to another journal, and that's okay, that's happening. Sometimes your paper is accepted very quickly, sometimes not. Don't be frustrated. Try to focus on your work, on what you think is important. And we need to tolerate these things with less frustration, but okay. Saying that, let me start. I am not going to put too many questions, but I would like to give you like a general idea of the structure of the questions. In particular, why resistive, relativistic, magnetohydrodynamic equations? Well, first, you have fluids, but also you have very, very important magnetic fields that should be included if you want to model things like accretion disks, active galactic nuclei, relativistic jets, or, for example, compact objects too. Most of these scenarios also needed a relativistic treatment. If not, they are not modeled very accurately. And this resistivity, if you don't include the physical resistivity in the system because of the numerical method, the particular numerical method you are using, you are going to include some numerical resistivity. Depending on the problem, this is not enough to model with the accuracy you want this scenario. So every numerical method has some numerical viscosity. You just need to know if this is enough for what you want. Sometimes it would be nice to include not the numerical resistivity, but a consistent treatment of the physical resistivity of your system. So which kind of equations you need to solve if you want to address this scenario? You need to solve a hyperbolic system of equations, so you have some propagation of information, plus some constraints, which are related to the divergence of the magnetic field and the divergence of the electric field. Dealing with the constraints directly is possible, but it's a little messy because sometimes depends on the specific details of the numerical grid or the numerical scheme you are using. So one idea, following Commissar of 2007, is that these constraints are encoded in two additional scalar equations that, together with the previous equations, form an augmented system of hyperbolic. So let's say from a numerical point of view, this is an easy way to deal with these constraints. At the end, the idea of these two additional scalar equations is that if at some point you have some violation of the constraints, this violation will damp very quickly and travel outwards of your numerical domain. So if you have problems, take your problems out, something like that. It's a way of control the potential violation of the constraints. So at the end, the structure of the equations is that you have the evolution equation for the electric field, evolution equation for the magnetic field, and evolution equation of other matter variables like velocity, density, energy, or variables related to this quantity. And these terms here that I don't want to specify are basically some source terms of the equations which are not problematic. So let's say, take your favorite numerical scheme that was working before adding resistivity, and the same thing is going to work. But the new ingredient, when you include physical resistivity, is this term here. So sigma is the conductivity of the system, that in general is not a constant value at all. It really depends on everything. And when I say everything, I mean everything you can imagine, maybe primitive variables, which are the physical variables of your system, but which are not the quantities you directly evolve. So it can be tricky to really derive or, let's say, compute this quantity in general. But it can be complex. But okay, whatever you want to put here in the model, then W is the Lorentz factor. The Lorentz factor is a quantity that depends on the velocity, this velocity field. Again, the velocity is not a variable that you directly evolve. You evolve some quantities that are called conserved quantities, which depend of these physical quantities. But, well, the Lorentz factor, you all know that the physical velocity of the system, and then you have electric field, velocity magnetic field, velocity electric. So the point is that if this, well, there are two things. First of all, the electric and the magnetic field have some wave-like behavior. So you need to take care about that if you consider Runge-Kutta low-order methods, because if not, it's like trying to control the orbit of a planet. You need to really control the orbit. If you solve all the components, you may find that the planet is orbiting another star after some time. So you need to control that there is a wave-like behavior between electric and magnetic field. And then you also need to control that this sigma can be potentially very, very high. And if this sigma here, or let's say effective resistivity, if you compute sigma times Lorentz factor, I call that bar sigma, the same quantity basically. So if this quantity is very, very high, you may end up with a lot of numerical instabilities developed in the system because of the presence of this steep source. So you need to do something. First, you need to do something because of the wave-like equation. I don't want to give you all the details, but basically, these papers in 2012 and 2014, they analyze a very simple time model of a wave equation. And then, so for a wave equation, I mean, you have some system that you can linearize, and the solutions are of oscillatory type. And then you can analyze the stability of the system in order to properly integrate in time these numerical equations. So you need to do something. If you put here a standard first or second order explicit Runge-Kutta, this is not going to work. You need to do something. I will tell you what. It's simple if you know what, but you need to know it. Let me say something. Why this paper appeared? I was doing numerical relativity, and all the codes used like 4th order, 6th order, 8th order. And I was like, why do you need this super high order? And then they were telling me, no, you need a lot of accuracy. You cannot do numerical relativity with low orders. Sorry, that's wrong. You can if you know how to deal with the development of numerical instabilities because of wave equations. And sorry, you have gravitational waves codified inside the Einstein equations. So I want to say a lot of things, not about my work, but in general. Don't believe everything that people say if you don't have a good argument. Or at least, if the equation or the problem is very complex, sometimes you think you understand more or less the system, but there are a lot of details that can be still explored. So the problem with this wave equation is not about the accuracy, it's about the high order. So if you put a Runge-Kutta high order method, then the system is stable and there is no problem. And that's why the people were using actually these methods. Well, one of the reasons. Then the second point is that, okay, this is when you include a finite conductivity, but one thing we should recover is the limit of our system. So in the case of infinite conductivity, this is called ideal limit, and the electric field is nothing but independent anymore, but the electric field can be written, should be fulfill this equation can be written in terms of the velocity and the magnetic field. So if you want to deal with a numerical method, you should be able to at least have some stable simulations with small and not very small conductivity, and also try to also recover the ideal limit with infinite conductivity. Is there something? Yes, there is something. There are a lot of things available. There is something called implicit or semi-implicit methods. Basically, the idea is that this part, which is not problematic, do it explicitly. This part that can develop some numerical instabilities because of the stiffness of the system, do it fully implicit. And then, if you have studied some basic numerical method studied, Euler implicit method is like a basic example in order to deal with this. So with implicit methods, you can have stable evolutions of some equations that in principle were giving problems with let's say, only explicit methods. But yeah, and this is one option that was actually implemented in 2009 by Carlos Valenzuela and collaborators. This is a mess. You can go to the paper. They need to do a lot of numerical tricks in order to deal with that. Why? Because these things, velocity, Lorentz factor, and resistivity, does not depend on the evolved variables, but on the primitive physical variables. This means you need to do a lot of iterative things in order to compute these quantities in an implicit way, and in order to invert the operator, because at the end you have this variable here evaluated implicitly, this quantity here, also this quantity, and you need to invert the operator, and this is really a mess. So you can go to the paper. I'm not going to put all the messy things, but it takes a lot of time. Carlos and collaborators did use the particular structure of the equations heavily, and also, so you have two things here, two problems. It's very expensive computationally. You are adding a lot of new things and a lot of new iterative loops, and that's a lot of computational cost. But also, because of the new iterative loops that you add, you can have convergence problems. So if you have quantities, for example, density close to zero, your physical density should be zero or positive. But if you have some iterative methods, you may not touching negative densities, which are nonsense. So it's not a problem only of expensive computational methods, but also convergence problems. You can have convergence problems in your system.
And how does the error propagate?
It depends a lot. It depends a lot. In particular,
huge errors.
Yeah, close to the boundaries, I would say. Yeah, close to the boundaries usually is the more dangerous area. You can do things, and in particular, Carlos use a lot the particular structure of the system of equations. But he had to, for example, compute a predictor for all the variables, then use this predictor to correct, and it was not easy. It was working, and I have to say, because the first person I think he managed to was him and collaborators, but it's really a mess, and it's not trivial at all to implement the idea. So what is my idea? I thought about this a few years ago, but I needed people to help me with the implementation. So it's a teamwork. The idea is that, okay, so these quantities, velocity, Lorentz factor, resistivity, if you do an implicit evaluation of this quantity, it's a mess, so don't do it. Just take the electric and the magnetic field and potentially the variables that you are evolving and allow only for these quantities in Lorentz to be evaluated both explicitly and implicitly. Moreover, there are other two elements that I want to mention. V squared, if you believe in general relativity or something close by, V squared is always bounded by 1. So in this part, this term should be dominant over this term. So I'm going to put this explicitly, but because of this argument. Then, even if this quantity is very, very, very small, you need to deal with the weight-like equation between electric and magnetic field, and which is the idea? The idea is to consider this kind of thing. So this part is coming just from the, I'm going to use finite differences method, but the idea is for general. So you discretize first order the time derivative, and then you do the same with your, let's say this source term is your favorite discretization of the spatial operators that you have. And then, what I mentioned, you allow this quantity to be evaluated explicitly and implicitly, also the magnetic field but not the velocity, and again, the electric field but not the velocity. Because of the argument I told you before, you can select C3 to be equal to 1, so actually this term will be evaluated explicitly. You need to choose C2 equal to 0 because of the weight-like equation between electric and magnetic field with the high value of the resistivity, and then because it's well, you can go to the paper, this term C1 equal to 0 gives you a lot of stability. What I mean, the The derivation of the values for the three coefficients can be found in the paper, but we do two things. We care about stability of the system in general at the stiff limit, and we need to impose the recovery of the stiff limit. I mean, we impose that this is going to be fulfilled in the numerical method, and we are going to impose stability of the system at the stiff limit. You can go to the paper and say the details. I don't want to give a lot of details, but let's say at the end you can choose T1 equal to 0, T2 equal to 0, and C3 equal to 1. If you do that, at the end, you can rewrite the system in this nice way, which is nothing else than an explicit method changing the time step. To take whatever you were doing before, and instead of putting in your numerical code this time step, you just need to change one number. And the inversion of the operator in this method is nothing more than one division. So instead of all the things you can go and check in the paper of Valenzuela, the inversion of the operator, let's say the extra cost in this numerical method is one division. And what you need to change in the numerical code is one number. Not so bad. You can try at least, not crazy to change the numerical code. An analogous derivation can be done for a two-stage second order minimally implicit Runge-Kutta method. The idea of minimal implicit is put implicit only the needed thing in order to get the stability, but don't get a massive numerical method. I want something to be cheap, to be fast, and to be, let's say, I want people having crazy codes of 10,000 lines of code or these kind of things. I want to convince them to use this method. So if I say to them, change your whole code, they are going to say no. If I say change one number, okay, let's try. You can go to the paper and see all the mathematical details, but it's not only about theory, but we need to check if this is actually going to work. It's working? Yes. It's working very, very nicely. I'm going to present you two simple tests that are included in the paper, and my plan is try to check with the people with these big numerical codes and also check in more realistic simulations. But these two tests are quite demanding sometimes, and it's also a way to control the first attempts of your new idea. So the first test is the so-called similar current chip. It's a 1D problem. You have analytical solution. We take the initial data t equal 1 in order to avoid any problem. And we use a CTL factor, the normal one of 0.8. This is quite usual for people doing numerics. We put a, let's say, non-small value for the conductivity, constant value, because we just want to check if it is working. You have an analytical solution, so you can really check if you are doing something crazy or it's more or less working. You can include some velocity, zero velocity or non-zero velocity. We also try in both cases with zero and non-zero velocities. This is in terms of velocity of light, so you are really adding a lot of velocity in the system. And the profile basically dissipates a little, and if you include velocity, it also moves a little. You don't see here, but we have the exact solution also with some approximation for different resolutions. The numerical solutions are so nice and so good that you don't see the difference, but basically we get second order of convergence and very nice results. This is the Y component of the magnetic field. This is just the spatial dimension, and this is the third component of the electric field. And again, you see that everything is as expected and quite nice and very, very cheap, numeric.
What are the two lines? What are the two lines?
This is the profile when you don't have velocity.
Okay.
If you just smooth it a little, dissipate a little, and if you include velocity, you see that it's the same profile, but including the shift. And we don't see any problem in both cases. Everything is working quite nice. So this is nice, but you may say, well, this is not very high number. It's not too bad, but okay. The second test is the so-called circular polarized alpha waves. It's again a 1D system. Here you evolve not only the electric and the magnetic field, but also the matter equations. And then you need to include the recovery of the primitive variables from the conserved and the evolved variables. You need to include basically the matter evolution. We are considering this initial data, it's a wave-like solution with this equation of the state of an ideal fluid. Well, this is just the initial data. We are using this value for the CFL factor because this is what it was used in other papers that they were trying to solve this problem, but you can really go much higher, which means a time step, a bigger time step. Yes?
What is the CFL factor from?
Okay, the CFL factor is Courant-free factor, I think, if I am not wrong. This is a factor that relates your time step in comparison with the cell size of the spatial discretization and the velocity of your system. So basically, if you want not to do something crazy from a numerical point of view, you need to know how fast things propagate, and you need to control that in your numerical domain. So this CFL equal to 1 will mean that I control in the limit my numerical domain in order to be able to reproduce the propagation of the information. So usually this factor is taking a little lower because maybe there are some non-linearities or some complexity of the system. So just to be safe, this is a control factor in order to be able to properly include the propagation of information of your system in the numerical domain. I hope I was able to. But it basically relates velocity of propagation of the velocity in the system, spatial resolution, and time resolution. Okay, then because this is a trace all in the time, this means that when you include matter, everything is a little messy, so you need to include a little of dissipation just in the matter sector. It's not about the stiff part, but you need to do it, and it's something common. People evolving let's say hydrodynamic equations. So what you have here is the Y component of the electric field and the Z component of the magnetic field and the Z component of the electric field. In this case, we are using a conductivity of 10 to the 8. That's high value, so that's really high value. It's quite demanding. There is not an analytical solution of this test, but we know what should we recover in the case of sigma going to infinity, which is the ideal limit. So the solid line here is the exact solution at the stiff limit. Let's say with sigma going to infinity. Okay, sorry, mathematicians, yes, this is not infinity, but it's quite high. So we should be close to these reference solutions, and it's something that we can use to control the stability and the convergence of our system. So you have here also different resolutions, and we get very nicely convergence to a solution which is very close to the reference solutions, basically what we expect. We have stable simulations, both in first and second order methods, and it's working very nicely. Let me mention that this is a very, very demanding numerical test because of this value for the resistivity. In our case, this was almost for free. I am talking one additional division. This is what I am including in your numerical method. Okay, so this is like the first example, and I hope I convinced you it was working. One of the things, well, this paper was published, but one of the requirements of the referee was put all this in a super big code. And I say, no, sorry. This is the idea. I don't want to spend 8 months writing a code that other people already have. So I'm going to talk to the people that already have the codes and try to implement this idea. I think it's nice to collaborate with people instead of trying to do everything from scratch and replicate things that I already know. Anyway, yeah, I think this is a very nice example, and I think it's really working very, very good. So the second example, let me go now to the second example. I'm going to try to explain which is the idea behind this method, and then I will finish with the general idea. So if you want to model the explosion mechanisms of a 𝗥𝗀𝗂𝗂 supernova, you cannot avoid to include a detailed account of the generation and transport of the neutrinos. If you don't include neutrinos in this system, the explosion of a supernova is not well modeled, and this is already well known now. In order to do that, you should, in principle, solve Boltzmann equation. And I'm talking about a 7-dimensional problem, which is almost crazy thing from a numerical point of view. So the people are doing some approximations or some approaches in order to deal with that, okay? I am not criticizing anything because it's what you can do, but let's say this was the problem I want to help solve. One of the ideas is to reduce the dimensionality of the system by performing a momentum space integration of the distribution. Okay. If you truncate this momentum at n equals 0, you have the so-called diffusion scheme. If you truncate this distribution, this momentum space integration at n equal to, this is called the n1 scheme. It's quite used. It's not perfect, but it's quite used. It's not so bad. And higher moments, you have a closure for higher moments. Okay, this is something coming from physics that I think it's okay. It's one. Let's say it's not so bad with the numerical and computational resources we have up to now. In the optical field regime, you have very different time scales of different interactions. And this, in practice, from a mathematical point of view, means that you have a steep source term in your evolution equations when the opacities are very high. Let me again show you like an structure, the structure of the system of equations, and trying to explain what I mean with this stiffness. So you have the 0 momentum, the energy, let's say, and the 1 momentum, let's say the flux of this momentum integration. The evolution of these two quantities have some source terms that are not problematic, so do whatever you were doing. Okay, nice, no problem. And then you have these collision terms. So these collision terms, you have speed of light, then you have these opacities, and then you have the variables you are evolving and this equilibrium profile. So the opacities here, again, are not constant values at all. It really depends on, the description of your system, and these opacities play the same role as the conductivity before. It can be very high, it can be very complex dependence on the physical variables of the system, it can be brilliant. And then this equilibrium profile tells you about the stiffening. When the opacity goes to infinity, you should recover, the flux goes to 0, and the energy goes to this equilibrium profile. Again, this equilibrium profile is not a constant value, and it can depend very non-linearly about temperature and density or whatever. You are the people expert in physics. I really don't know a lot of details about that. But it's not a constant value at all. What happens if these opacities are very, very high? Again, as before, this term is a stiff source term, and if you don't do anything, you are going to develop numerical instabilities very, very easily and very, very fast. There is something you can do, which is a so-called IMEX-like method, which is basically take this explicitly, take all this thing implicitly, and try to solve that inversion of the operator if you can. Even numerically, it's a mess and it's very complicated. This is an idea, very, very well known in applied mathematics, and the fathers of this IMEX idea are Palesky and Russo from Italy. They're really very, very important people in this field. Why I say IMEX-like method? Because some people, Oliver Diaz and collaborator in 2015, they say we are solving this system with some IMEX-like method. And say, IMEX-like? Okay, what's that? Because if you want to use, let's say, purely IMEX methods, inverting this operator, doing everything here implicitly, opacities, equilibrium profile, and everything, is almost impossible. It's very, very big. So I say, what are you really doing, people, when you say IMEX-like method? First, and then second question, well, you know, Martin Oregoninger is in the building in front of me. He's doing core collapse supernova explosions. He wants to include neutrinos. Martin, you already have the code. Why don't you try this idea? It's not very difficult to modify the code, blah, blah, blah. And he told me, yeah, it's not a problem. Come in 1 week and let's see what we have. 1 week later, he told me, Isa, your method is working. I say, really? So fast? Well, actually, we were already using it. Say what? Okay, people in physics are super practical and they really work a lot. And sometimes you find the solutions even without knowing why. So they were using a very good scheme without the mathematical framework understanding. Okay, not so bad because I was very happy. I was, oh, the method is working, but okay, you should know why it's working. No problem, no problem. But what basically, the point here is it was so difficult to evaluate implicitly all these source time that basically they were trying a few things, and one of them was what? What they were doing and what I proposed, the same as before. We only evaluate implicitly these two terms here, not the opacities, not the equilibrium profile. You allow, you do the computations, you impose a stability of the system at the steep limit, which means this opacity goes to infinity. You impose, and this is very, very important, that you need to recover F goes to 0, E goes to the equilibrium profile. These are two conditions. You need to include the two things, and you end up with very nice values for the coefficients. I did the inversion of the operator for you, which means only one division per stage and variable, which is not so bad, no? Not a lot of complexity. So basically, you take your splicing method, you change this time step by an effective time step. If you go to second order, you have a first stage similar to this one and a second stage of this way. In a purely explicit method, here you have 1/2 delta T over 2. Okay, change these three numbers, but by whatever I told you, it should work. Then you put this in your system and see what's happening. Spoiler is working super nice. It's working so nice that we want to check if we impose stability but not recovering of the steep limit, so you can have stable simulations but wrong simulations in purpose. The numerical scheme was doing indeed that. The simulation was very stable, but the limit was not the right, no? The value at the end of the simulation was not the right one. And this is something we knew from the analytical analysis of the numerical method. So, we submitted to the paper, it was rejected. And one colleague from mathematics told me and said, Isa, you know what is the problem? You proposed the method. You went directly to the core collapse supernova simulation, whatever, so mathematicians are not happy. They like a simple test to control convergence and stability and blah, blah. And I say, okay, so let's do it. So I'm going to show you what is now going to be included in the new version. This is not included. Samuel, Martin, we are performing simple tests just to check that convergence and stability in a control scenario is actually obtained. So there is one simple test taken from test 1 of this publication. It is called the diffusion limit, where you have this approximation. It's a spherical symmetry, so 1D problem. You neglect one opacities, but you don't neglect the other opacities, so you are still simple case, but not trivial. And the nice thing is that you have an analytical solution, so you can really check that you are doing something nice and not crazy. This is the analytical solution. You can plot everything, and this is what we obtain. Because we have the analytical solution, we use that at the boundary conditions in order to avoid additional error coming from let's say from boundary conditions. We play with a small, let's say not so big opacity and very big opacity. You have the solid line is a star solution, and the other lines are different resolutions. Again, here the same. And what we found is that even if you use first or second MIRK, so Minimally Implicit Runge-Kutta method, you end up with a very nice convergence. First order in the case of not so high opacity, and second order in the case of high opacity. There is a lot of literature about order of convergence and implicit method. I can give you more details, but basically this is not crazy. This is actually something that's happening. If you go to a very symmetric profile, you can increase order of convergence. If you are in a transition phase, let's say I have designed this method, taking into account only, let's say, 0 and infinite opacities, but nothing else in the middle. So if we have a reduction of the order of the convergence, but still a very nice convergence, this is, let's say, this happens, and this is found in applied mathematics common. But when you see this very nice convergence, we can deal with all the numbers you want. From 0 to infinity, you can put that in the numerical scheme, and we get very nice, stable, and convergent simulations. So I hope mathematicians are now happy, and they are going to answer the paper. And this is actually the thing we did before. It was directly applied this method to a complex core collapse simulation. Please go to the archive reference in order to check that all the important interactions that dominate the dynamics are included. Basically, I am not an expert in this part, but Martin 𝗥𝗲𝗂𝗵𝗵 was the person including all these interactions. Here you have, if I am not wrong, a fraction of electrons, all kind of particles. I don't know this thing, sorry. This is luminosity of neutrinos. This is the radius, the location of the radius of the shock and the proton-neutron star, and these are energies of different neutrinos. Okay. This is important for you because you are doing physics, people doing astrophysics. From my point of view, it's more about comparison and reference solution. So here you have different solutions. The first line is the reference solutions that they were using and that I am going to consider as valid, good enough solution of the system. And then the second line is the first order method, and the second, the last 3 lines and second order method, because there is still some freedom in the values for the coefficients, and we wanted to check if this analytical study was accurate enough or not. Also, we play what I mentioned before. You can put stability, but not the right recovery at the stiff limit, and you see that numerically you got that. That was really impressive.
You mentioned that they were using already
the
same method.
It's not the same exactly. It's a little more sophisticated method with second order. Let's say a little more sophisticated method, but what I want to say is that this is what they say is a reference valid solution. This is a little more detailed, with more stages and with more smaller time step. So let's say this is my valid reference solution, and that's why I put Runge-Kutta 2, because it's not actually implicit or IMEX. It's something like explicit with a lot of care. Okay, but this is something I didn't like too much at the beginning. You put IMEX like, what is this like? No? Basically, it's that thing. You say explicit with some details that guarantee you that you are not doing crazy things, and also they validated with other numerical simulations, and at the end, for me, this is like the valid solution I should record. But there were a lot of tricky things inside that, including a lot of computationally costly numerical tricks, let's say in that way. What is the nice thing for me? Everything overlaps. So instead of doing whatever crazy, difficult, computationally cost thing, take one division, release one division per variable and states, and you recover the same. And this is just to explore that the analytical analysis was in agreement with the numerical results. In the paper, you can find more details about playing with these coefficients. and check it that I expect that this is going to be unstable if I take these values, I go to the simulation, and surprise, the simulation is unstable. So we really understand with a very simple analysis. I am doing the analysis at the state limit. I am not controlling this transition, but let's say I took strongly what's happening at the two borders, at the two limits, and in the middle, that was enough to control. And it was working. It was working very nicely. We have a stable and accurate results using first and second order methods with respect to this reference solution. This is what I mentioned. We understand what's happening about the stability and recovery of the sleep limit. The computational cost is really almost nothing. So it's very, very easy to apply this method, even if, let's say, independently of the complexity of the opacities or the equilibrium profile or whatever you do in the matter variables. This is actually very, very cheap. And, well, it seems that there are people interested. There is a workshop July next year in the Institute of Computational and Experimental Research in Mathematics. This is the term. There is a workshop already approved called Solving Boltzmann Equations for Neutrino Transport in Relativistic Astrophysics. And there are two applied mathematicians in the list. This is me. And the other one is 𝗙𝗲𝗂𝗂𝗂𝗂. Not so what? I mean, it's one of the fathers of the IMEX method. So I say, come on, this is going to be accepted soon. Don't worry too much about the projection. And then you have Carlos Valenzuela, and also David Radice, François Foucault, and Steve Liebling. These are very, very good people doing numerical simulations of these astrophysical scenarios. The problem of solving Boltzmann equation on neutrino transport is very expensive. So the idea is that, great idea, put together people doing applied mathematics and people doing astrophysics and try to make them to talk a little and check if there are good ideas from applied mathematics and good motivation from astrophysics and to collaborate. So I hope to finish a few things and to publish this paper soon before the workshop. You are all invited if you want to come. There is also the possibility of attending remotely. And I just wanted to put this thing here, even if your field is different, because in this institute there are a lot of collaborations between mathematics and other fields, also mathematics and particle physics. If you are interested, let's say, in trying to solve some challenging problems in your community with interactions with applied mathematicians or mathematicians, have a look to this institute because they support a lot of this kind of collaborations. And well, I hope I convinced you the idea was not so bad. And let me now give you the general idea. If I talk to mathematicians, I say this in a different way. Let me say first the mathematical way, and then I will translate like the language I think people use in physics. So the general idea of the method was solve hyperbolic equation with a series terms which can be somehow linearized with respect to the conserved evolved variable. Okay, what this means, you need hyperbolic equations if you propagate information. And in physics, most things are propagation of information. If it is not hyperbolic, then maybe there is something missing in the system. Then Steve shows them. If you have friction, collision terms, resistivity, viscosity, these kind of things usually are modeled in physics with some steep source term. Maybe collisions in your case would be more natural, but there are a lot of examples. And then the system, I need the system, so this is a hyperbolic equation system with the source term, a part which is not problematic, and another part that can have this 1 over epsilon is the sigma, or the opacities is this factor that can be potentially very high. And then you have to pass this part comes from, let's say, the equilibrium profile you want to include. And in this part, you need, and this is the last thing, you need to be able to perform a linearization of this part with respect to evolved variable. So this is what you did, for example, here. The linearization is, this is the variable, this is the thing multiplying the variable, this is the variable, this is whatever the factor multiplying the variable. These factors are not necessarily constant, and it's an art to understand how you do this, but you need to know a little of your system in order to check what is the first linearization. But come on, doing Taylor expansion or some kind of expansion in physics and take the first order, I mean, this is something that is done in a lot of systems in physics. If a system cannot be linearized, it's not, let's say, in most of the cases. So this is the hypothesis from the mathematical point of view are there, and for a physical point of view, it's not a crazy hypothesis in a lot of examples. The idea is that in order to, instead of evaluating implicitly all these terms, you only evaluate implicitly this variable, so the inversion of the operator will be very easy and very direct. And I show you that this idea is working in resistive relativistic magnetohydrodynamics. It's also working very nicely in M1 neutrino transfer equations, but I'm pretty sure that this kind of ideas can be applied to relativistic force-free electrodynamics or other kind of equations like shallow water equations and other equations. And maybe you can also provide me very nice examples that I don't know, so I will add this example into the list. I hope I managed to give you like an idea. You can go to the papers and check the stability and the mathematical analysis and so on, but I don't want to bother you with these details. Thank you very much. Thank you for your attention, and thank you for this third start invitation of the seminar. Thank you very much.
Very much, Isabel. Questions? No questions for Isabel?
In your last graph, why the line of F24442 looks a little bit different from another?
This one here, actually, just in the middle of here. There is some slight difference because of the method. The method is first order, second order. You expect that the second order is more accurate than the first order. So if I increase the resolution, spatial resolution, I will get convergence to the same reference solution. But the point is that these simulations are very, very expensive, so you need to get a compromise. There are slight differences, but they are coming basically from some difference in the numerical error, but with more resolution, you get convergence, nice convergence.
Bueno, Lucas.
No. The first question is, early on you mentioned that you use these auxiliary equations to enforce some constraints.
But this is only for the physical system.
Yeah. And you said that you have the system that it drives out violations. What happens if you have a violation already happening at the numerical level to the conserved quantities that we expect that the system conserves automatically without the constraint? Will they get also violated and then driving out the settles the system, say, at a different energy or something, one of these conserved quantities?
What you clean is the violation in the divergence. So if you have some error in the variable itself, that's not the procedure. Maybe you need to go to high order or increase the accuracy, the resolution, the cell smaller, let's say, a smaller cell. But what you include in that with these additional scalar equations is the cleaning of the divergence of the field. And basically, you add a wave-like equation of this violation that dumps and travels very fast outwards of the numerical domain. So you are not cleaning, you're not warranting that the variable itself, the ball variable will be nicely recovered, but you just clean the divergence. But the other part is more like add more accuracy, solution, or higher order. So these are two different things. But this is the physical model you decide to solve.
Yeah, compared to other methods in the literature, how fast is how much do you win with your...
Yeah, okay, so since I didn't want to implement this ugly scheme, the people told me, how much are you winning, no, in time? First, there is not a number, because in my case, the computational cost is the same as a purely explicit method. But if you need to, let's say, if you compare with IMEX methods, which are a standard tool now available, the inversion of the operator will depend strongly on the complexity of this equilibrium profile or the complexity of your conductivity profile. So let's say, the more nonlinear, the more complex the source term is, the most computationally costly is the inversion of the operator. In my case, it is the same always. So there is no a fixed number. It depends on the complexity of the system. But I talk to people in Italy, and they say that when they go from explicit to IMEX methods, the simulation is 3-4 times slower. So instead of 1 week, 1 month, like a reference. So in my case, I will go, in principle, this depends on the complexity of the system, but let's say some reference time that people doing this IMEX are telling me, from 1 month, you go to 1 week, which is a lot, I think. And because, I mean, these simulations, the simulation of these simple texts are very fast and more or less okay. But these realistic simulations are very expensive, and sometimes we are talking about weeks or even months in supercomputers, this kind of thing. So it's an amount of time that you may consider important.
Not negligible.
Yeah, exactly. Let's say that, but there is not a fixed answer because this implicit operator, the inversion of the implicit operator, it depends a lot on what you need to infer.
More questions?
I have another question. It's something which whenever I see people working with Runge-Kutta, I wonder, why do people use multi-point methods and don't use more multi-step methods, where you don't throw away the intermediate calculations, but you keep them? It sounds at first time like you would save me automatically in the fourth order method, you only do a quarter of the evaluations.
Let's say, they are just different options. Sometimes, well, let's say, in this kind of simulations, you don't take all the time steps. That's impossible if you want. Maybe if you want to do a movie, you say a few time steps, but in general, you don't take all the time steps because that's a lot of memory, that's a lot of information. There is not a strong option, or let's say opinion. In my point of view, you can use several intermediate steps, or you can use previously time steps. But at the end, if you use previously time steps, maybe you need to reduce the time step in order to be accurate. And if you use several stages in one time step, maybe you can use a larger time step. But at the end, they are just two different options. There is not a fundamental reason, I would say. It depends on how you save data, how you compute data, how you, let's say, the architecture of the computer you are using sometimes also important. Or maybe tradition, your code is written, you have 10,000 codes written with this option, and say, come on, I don't want to change the 1,000 lines of code. Yeah, no big preference, I would say.
The Runge-Kutta only evolve the conserved variables.
Yes.
How do you evolve the primitive ones?
You don't evolve the primitive variable. There is a 1-1 bijection between conserved and primitive variables. The conserved variables are written explicitly in terms of the primitive variables, but in order to do the other way around, you need to do some iterative methods in general. So you know that from a point of mathematical point of view, the Jacobian of the change of coordinates is different from 0. So you know you can do the inversion, but it's not easy at all. There are a lot of ideas and tricks in order to do that. What I say is that do once per time step what you need as minimum, but don't do it more times. There is no need to do this more times. If you do IMEX, each time you try, let's say, the inversion of the operator usually is performed with some iterative Newton-like method, let's say, and in each step of this iterative method, you need to perform inversion of the variables from conserved to primitive. So that's super expensive. In general, with some simple models you can play, but more realistic equation of states, that's very complicated. So I would say that's enough complicated to add more times this recovery. So it's possible from a mathematical point of view. You need to do usually iterative methods in order to do it in practice. More questions? Yeah, I'm super happy to have questions.
No, I understand that these methods can be combined with adaptive time steps or adaptive measures to really put the emphasis only on the part where the physics is interesting and not sort of like on the outer part of the system or whatever.
Yes. Yes. Instead of having, let's say, this delta t everywhere, well, the delta t, but maybe you can have this discretization of this operator can depend on the resolution, different resolution. Maybe you don't want to use Cartesian coordinates, but spherical coordinates with a logarithmic radial grid in order to put more resolution in the center, not so much resolution. That's nothing to do on how you discretize this operator here. This is something about what happened with the stiff ingredient. So, yeah, let's say I don't touch that part. In principle, I don't see that there is any problem here.
Yes. Well, if not, thank you very much again, Isabel. It was really
Thank you very much.